All right, so now that we've got a basic understanding of the three-dimensional shape of cyclohexane, we can take a look at some conformational analysis. And so one thing we have to realize is that there's a difference between the axial and equatorial positions. And this picture out of your book does a really good job of demonstrating this. So in red are these axial substituents. And so you can see that these axial substituents are actually much closer to one another than these equatorial substituents. The equatorial are actually much further apart. And so what this causes is the axial position being more crowded. And so, for example, if we were to draw a cyclohexane and then add a, let's say, a methyl group, draw this in purple, a CH3, and then a hydrogen, right? Think about which one of these groups is bigger and which one of these groups is going to prefer to be axial. So we can draw some of our chair conformers. And we can put this CH3 anywhere we want. So for now, I'm just going to draw it here as being axial, and then this hydrogen is equatorial. And so if we think about what else is here, there's some axial hydrogens here and here. And so this methyl group is actually quite large. And so there's going to be some steric strain from the methyl group interacting with the hydrogen groups. And so let's check out what happens when we do a ring flip. So this carbon is going to flip up over here. This carbon is going to flip down here, and we're going to switch axial and equatorial. Right, so this carbon is our carbon of interest. It's going to come up here, and we're going to switch axial and equatorial. So now our CH3 is equatorial, while the hydrogen is axial. And so even though there are axial hydrogens elsewhere, here and here, right, these groups are much smaller, and so there's no steric strain there. And so if you were to look at what conformer cyclohexanes or this methyl cyclohexane adopts at room temperature, 95% of the compounds will be in this conformer, while it only spends 5% of its time in this chair conformer. And so this is similar to the alkanes and the Newman projections, right? It's these big things want to get as far as possible. And in this case, as far as possible means being equatorial. And this is specifically called a 1,3 diaxial interaction. And it's disfavored. Why 1,3 diaxial? Well, if we think about this structure right here, I'm just going to remove some of these extra drawings. If we were to number these carbons, right, 1, 2, 3. So we're talking about the interaction between the thing on carbon 1 and carbon 3, and they're both axial. So 1,3 diaxial interaction, and again, it is disfavored. And then again, here's just a picture from your book, just demonstrating this in a little bit neater fashion. And this one actually has a nice little model that you can take a look at and see. And again, what you notice is that this carbon in the back becomes this carbon in the front, and the axial and equatorial positions flip.